final lecture on earthquakes, earthquake lecture number 4, we are going to get into the hazards and how we can prevent them to protect humans and our infrastructure. Today we're going to base this lecture based on lists, and our information, if you're following along in the textbook, is in chapter 9. And as we get into this lecture on, let's say, hazards and their prevention, we should start by thinking about where people live. And here's a map of population density for part of the Earth. And what we're going to emphasize now on this is, where are their faults? Where are their plate tectonic boundaries? And there are big ones. Look at that population density. And this is where the Himalayas are, because India is slamming into Asia. Japan is on a fault. Taiwan's on a fault. All of Indonesia is on faults, right? There's faults through, and here. As Saudi Arabia is slamming up into Eurasia, we have tons of faults. There's faults. I guess what you could see from this diagram is, because of plate tectonics, there are faults, and people live on those faults, sometimes in the highest densities, and therefore earthquakes present an ever-present and awful disaster that can impact humans with suffering. And so we're going to go right now through the main quake hazards. 4 quake hazards, right? It's not the P wave or the S wave or the surface wave that actually does the killing. Although rarely the waves are so strong they can throw people in the air, it is not that. It's the secondary impacts. And we'll just start with number 1 here to demonstrate that. Building collapse. Right? The earthquake waves don't kill you, but it's the building falling upon your head, I shouldn't joke, that causes this. And in fact, building collapse is the majority killer and the majority cause of financial damage. It is produced by S waves and surface waves that have amplitudes, all right? So like between like 1 centimeter and more than that, more than a meter, I guess we could say 1 meter. That's how big the ground will actually be shaking in order to cause buildings to start to fall. The substrate matters very much, right? Don't build your house on the sandy land. Build it on solid rock. That is key for earthquakes. And so we're going to say substrate matters, where rock foundations are strong and safer, but if you're built on sediments and sand, they can actually amplify the shaking. And so we'll say sediments amplify shaking. The things that are going on during building collapse, it's things like bricks fall, or other like facing facades on the outside of buildings. You can have floors collapse, and then you're stuck because the floor fell on top of you. Bridges collapse. All right, these are the things that are happening under this idea of building collapse. And really, one thing that's important, especially in places in the world that are built of wood and not concrete, is that fires occur. The earthquake doesn't make the fire, but ruptured gas lines and sparks produce fires. And this is famously from the 1906 earthquake of San Francisco. Only 500 people died, but 250,000 people were left homeless, because at the time San Francisco was built from all those majestic redwoods that had been cut down in the centuries beforehand. Now, to mitigate building collapse, there are things you can do, and it's all about construction quality and being strategic about how you build. And so one thing you could build into the bottom of a building is a dampener. All right, so you see this rubber thing between the foundation and where the building construction starts, which could accommodate some of the shaking. Or over here we see somebody putting in braces. And it's these braces and dampeners that can lead to building stability. But one thing that really, another one is rebar. And I say this because in developing nations, concrete is the killer. And if they can put rebar in that concrete, which is steel that will help hold the concrete together, the buildings will be so much stronger. All right, number 2 in our list of hazards is liquefaction. And this ties in to groundwater and sedimentary rocks. And the name of liquefaction is totally appropriate. It's just when solid earth turns into a muddy, watery slurry. Like quicksand. Solid earth turns into muddy slurry. And so if your building is built on something that was solid earth, but then turns into quicksand, the building can just topple over. The other thing is that it can, it can amplify earthquake waves. Why don't I just show you this in an image first? This is a cartoon from a textbook. All right, and so here's how it shows liquefaction. We've got these buildings. It's on the coast. In fact, we should emphasize this. It's coast. And this material, look at this word here, topsoil, sand. What is that? That is sediment. The other thing we can see in this picture, it's emphasized here in this circle, is that there is groundwater in the pore space. And when shaking occurs, look what's happened to all those particles and the porosity. The porosity increases significantly. The grains are no longer touching. We should say that. Grains no longer touching. And if the grains are touching, then the solid material is now a liquid, which allows for houses to collapse and like all these little springs to occur on the surface. Look up liquefaction video earthquake on YouTube or just a Google search or Microsoft Bing search, and you'll see really how amazing it is to have soil liquefy. Okay, so now number 3 in our list is landslides. Landslides always occur if there are slopes and topography in a land with shaking. And so we could say is shaking destabilizes slopes. There's not really much else to get into anymore. What is a landslide? It's mass wasting. We already spent a number of lectures on mass wasting and creep and slump and debris flows, debris avalanches, rock slides. All of those could be included in this idea of landslides. How do you mitigate? Oh yeah, because we should mitigate each of these things. To mitigate, which means protect against. It's really about landscaping and like understanding topography when you build. Can you put in retaining walls near highways, things like that, to help control the slope, drain the water? I forgot to tell you how to control liquefaction. The best way to control against liquefaction, I'll put a little star here. All right, this is our mitigation star, and it would be to build on rock, or you could say limit build on sediment. And now our final type of natural disaster that occurs in response to an earthquake is a tsunami. I spelled it wrong. Tsunami. And 20 years ago, these had not gotten much notoriety, but then we had these awful disasters in with the Indonesia quake in early 2000s, and then the Japan quake in 2000 in the mid 2011, I believe it was. And we've learned so much about tsunamis since. The world has not forgotten about them anymore. And it is not a wave. It's more like a wall. But even better than wall, I think we should put in the word plateau. This is a plateau of water. And that plateau of water is caused by seafloor displacement. So when the earthquake moves, imagine the scarp, right? That's the offset of the Earth's surface. But if the scarping occurs underneath the ocean, we're going to displace a lot of water. And it acts like an increase in sea level. Acts like increase in sea level. So when the wave hits, the tsunami wave hits, you think it's just going to be a single wave, but it's not. It's almost like this river of water that just floods a coastal region. I'll make a drawing here, and of course this drawing is limited based on my ability, but imagine, let's say we have a subduction zone, and there's an asperity that's locking the two plates together. And as they are, this subducting plate is like pulling down the lithosphere, and this plate is probably stuck to this other plate by some asperities, and so this plate is being pulled down. But then when the earthquake occurs and the slipping happens, this plate pops actually back up to the surface by, I don't know, maybe by 10 centimeters. In the case of Japan, on the order of tens of meters. And if you are displacing that much water in a vertical way, there's a new sea level sitting above, as a bulge above that plate that's just popped up. And that wave then will move in all directions across the ocean. Initially, that wave might only be centimeters tall. But then as that wave approaches the shoreline, it can actually increase in its height until it's meters tall. And if you want to search tsunami on YouTube, and you'll see really like devastating and awesome videos of tsunamis approaching coastlines. How do we mitigate against tsunamis? These are huge events that you can't stop if they were to occur, but what you can do is you can predict and you can warn. And so the best we can do for tsunamis is have these things like ocean buoys, which then communicate across an ocean where, it's as simple as basically there's a bobber floating in the ocean, and when the wave rushes past this buoy and makes it go up just by a little bit, it will send a signal to a satellite, which then sends that signal to computers, which then alert the whole world. All right, so that's our 4 different types of warnings. I will say this, there is no way to predict, no prediction possible. Science is trying so hard, but charlatans are also trying so hard to convince you that it's possible. Scientists are trying to find a way to make it possible, but they haven't yet. And so for predicting earthquakes and saving people, the best that we do in some ways is a map. And here's a map from the United States Geological Survey, and in colors it shows areas of hazard. And so if we can map where people have faults, obviously along the San Andreas, along the coast of Cascadia, maybe people don't know about earthquakes in the mid area near St. Louis, but if you know that there is hazard, then you can build safely so that these buildings don't collapse. That is a key towards mitigating disaster on a big scale. One of the neatest developments in recent years to make earthquake safe is something called like a shake alert system. And it's built based on this idea that P waves and S waves have different travel speeds. And so if the P wave, you can pause this if you just want to read through it. I know there's a lot of text here, but we're going to call this a P wave warning system. And with this P wave warning system, the computers or even cell phones detect a P wave, and they know that's not too dangerous. It arrived fast, but what's coming next are the S waves and surface waves. And that will send this alert that will shut down trains and give people in buildings a chance to brace themselves. This has been successful already. Japan did an amazing job with one of their earthquakes in recent years, where they gave people up to a minute worth of warning before the big shaking occurred. But the type of warning is going to be anywhere from 0 to 60 seconds. But even 3 seconds can help you get under a table and perhaps save your life. All right, that's it for earthquakes. Moving on to magmas and volcanoes next class.